Have you ever wondered why a medicine works for some people, but not others? Or why a policy succeeds in one city, but fails in another? The answer often lies in understanding causation, not just correlation. Today, we're diving into a groundbreaking study that uses machine learning to untangle these complex cause and effect relationships, even when data is scarce. Let's start with a simple question. What does it mean for something to cause an outcome? Imagine you take Tylenol for a fever. The drug and the fever are correlated, but we don't take Tylenol because of the correlation. We take it because we believe it causes the fever to subside. This belief is captured by a concept called Probability of Necessity and Sufficiency, PNS, a measure of whether a cause is both required and enough to produce an effect. But here's the catch. Estimating PNS, PS, and PN usually requires both observational data, what we see in the real world, and experimental data from controlled trials. Think of it like needing a recipe's ingredients and the cooking instructions to replicate a dish. Yet in many real-world scenarios, we don't have enough data for specific subgroups, like a rare disease population or a unique demographic. Traditional methods struggle here, leaving gaps in our understanding. This is where machine learning steps in. The researchers behind this study developed a clever approach. They trained models on subpopulations with ample data and used that knowledge to predict probabilities for data-scarce groups. Imagine teaching a chef to bake a cake using recipes from a well-stocked kitchen, then letting them recreate it in a kitchen with missing ingredients. Their secret weapon? A multi-layer perceptron, MLP, with a special activation function called Mish. Think of it as the chef's secret spice, giving the model just the right edge to make accurate predictions. In tests across thousands of simulated scenarios, this model achieved near-miss accuracy, with errors as low as 2% when predicting PNS for 32,768 subgroups. That's like baking a cake with 98% precision, even when you only have 2,000 recipes to learn from. But why does this matter? Well, these probabilities aren't just academic. They're critical for personalized medicine, policy decisions, and fair AI systems. For example, if a drug works for 70% of patients but fails for others, understanding why could save lives. And when data is limited, machine learning acts as a bridge, filling gaps without sacrificing accuracy. The study also introduces the first synthetic dataset with multiple structural causal models, SCM, like a toolkit for testing cause and effect theories. This opens the door for future research, making it easier to validate new methods. Now, let's dig deeper into the technical heart of the research. The team didn't just build a new model, they tested how different approaches handle tricky scenarios. They created fake data, like a controlled lab experiment, to simulate real-world problems. Why fake data? Because it's like a playground where researchers can test ideas safely. They tweaked variables, added hidden influences, and saw how well models could still find the truth. Here's where it gets cool. They compared 3 types of models. One acted like a confounder detector, another uncovered mediators, the hidden steps between cause and effect, and the third predicted outcomes. Imagine trying to figure out if a new drug works. The confounder model checks if other factors like age or diet are messing with results. The mediator model sees if the drug affects the body through a specific pathway, and the outcome model guesses if patients get better. But here's the twist. They didn't just focus on accuracy. They asked what happens when data is incomplete. Their experiments showed that even smart models can trip over gaps in information. That's why transparency matters. If a model's wrong, we need to know why. And let's talk about the numbers. They tested activation functions, like the brain of a neural network. Turns out, one called Mish outperformed others, especially in tricky cases. It's like a supercharged version of RayLU, the go-to function for many AI models. But here's the kicker, no single tool is perfect. The best results came from combining math, creativity, and a healthy dose of skepticism. Now let's unpack the model comparisons. The researchers tested GBDT, MLP, random forests, SVMs, and even transformers, evaluating their performance on predicting outcomes across 2 ranges, lower bounds and upper bounds. Their confusion matrices, those grid-like charts, showed how often each model got the right range. For instance, if a model predicted a value between 0.7 and 0.8, how often was the real value actually in that range? Most of the time, the numbers clustered in the middle, suggesting models were confident. But look closer. Some models, like GBDT or random forests, faltered at the extremes, their predictions spreading out like a dart thrower losing precision. The scatter plots on the right told a similar story. Each dot represented a data point, true value versus predicted value. A perfect model would line up along the diagonal, but real-world models had scatter. GBDT's points clustered tightly around the line, like a skilled archer hitting the bulls. SVMs. Their dots were more spread out, especially at the edges. Think of a pitcher who's consistent in the middle of the plate but struggles with fastballs down the tunnel. And here's the twist, the transformer model. It's the gold standard here. Its scatter plot showed a tight cluster across the board, suggesting it's both accurate and reliable, no matter the value. It's like a marathon runner, steady, consistent, and ready for any challenge. But here's the real takeaway. This isn't just about flashy tech. It's about ethics. The researchers warned about misuse, like AI being used to manipulate or harm. They shared their code, data, and even their mistakes, setting a new standard for open science. It's a reminder that progress isn't just about solving problems, it's about asking, what happens next? So the next time you hear about AI breakthroughs, remember, the real story isn't just in the results. It's in the questions asked, the data used, and the courage to admit what we don't know. Thanks for watching, stay curious, and let's keep exploring the hidden logic behind the data.